Machine learning from scratch with Python is actually pretty simple if we know what we're doing, although it's also simple even if we don't know what we're doing. I actually split it up into two main components. One is the inference, where we are able to have the AI predict outcomes based on its trained data. So we've got our prediction section, and then we have our training section, which is the other side of it, where this is the machine learning part, where we're teaching the AI, and this is the learning phase. So we're going to walk through some of the most foundational concepts that are necessary for writing your own machine learning from scratch using Python. I also am using NumPy. It is a nice library that eliminates the need to write a lot of for loops, and it comes with some nice built-in math functions that just make things simpler. For the most part, we're just using the math functions, sort of like multiplication, dot product, when we're running math operations against matrices. This just simply eliminates the need to do for loops. We could do it without NumPy, and we can write our own for loops, but it just makes it so much more readable when we don't have to do for loops. So let's just start with the very basics. Machine learning is all just matrix multiplications for the most part. What we're doing is we're taking two matrices, multiplying with each other, and then we get an output matrix. Input matrix is A. The input matrix is the information that you're feeding into the network. So for an LLM, this is a bunch of text data. For image recognition, it's going to be a matrix of all the pixels, so you can feed an image in. For audio data, this could be the waveform all put into a matrix. And you're probably not feeding the entire song or conversation. You're feeding just segments at a time into the matrix. Because if you fed the entire song, you couldn't. We just don't have enough memory for computers to load entire songs into this format that would be able to be understood through an AI model, because these AI models can take a lot of memory. For the most part though, if you're training it on something fairly straightforward and simple, we can create a whole bunch of small models, optimize them really well, and then leverage the best models where needed for various tasks. The second matrix here, matrix B, these are the model weights. You've heard about the number of parameters, like LLMs are like 7 billion parameters. Well, that's matrix B right here. It's matrix B. C is the output. So this is actually just the simplest version that you're looking at an AI model right here, essentially. This is it. It gets more complicated when you add more weights, because you can add additional matrices. So you can have, that's the deep learning part. The deep learning part is you just add another matrix. So you've got one matrix, that's regular machine learning. Multiple matrices, that's deep learning. We can build our own machine learning AI framework from scratch using Python. We'll walk through right now just the beginning part of the machine learning process. And we need to be able to take input data, run it through a matrix, usually through matrix multiplication, and then we get an output answer or a result. And this is the first part for machine learning. You need to be able to do that. It's also the part that you use after the machine has been trained. Whenever you want it to make its inferences or predictions, you will use this input process as well. So this is the feed forward aspect. So looking at this predict function here, what we've got is one variable here. You can ignore self, because that's just a class construct. For now, we are using just one input, and that's the features. The features in this case are going to be the image data. So like the pixels, so you can have like a 100 by 100 pixel image. That could be the features. It could also be text data, right? So we've converted every character into a floating point number, or just the ASCII value of the character, and then we put that into an array of numbers. That's the features. And then we run that through a forward pass, which takes all the layers. Now, what are the layers? Each layer is just a matrix. It's a matrix with random floating point values, and you can specify how big that matrix is. You might want that matrix to be, pretty small. Or you might want it to be really big. And those large language models have really big matrices, because they need to remember a lot of information. So you can have really big matrices. Usually we don't need that big of matrices, so you can shrink that matrix down. And then when you have multiple matrices, you can stack them on top of each other. What we're doing is we're just doing matrix multiplications with the output for each. So let's look at it like this. So here's our first layer. Here's our feature data set here. matrix A, that is like, say, the pixels data, right, or a picture. We do the matrix multiplication against our layer weights, and we get an output. Then we take this output, run it again through the second layer, and the C becomes A. B is the second layer now, and we'll run the matrix multiplication on that, and we get another output. And then we do it again. And then we just keep repeating that process for as many times as we think is necessary. Usually about 3 or 4 is a good standard. You can do more. There's diminishing returns after a while. But you do get improved accuracy and learning the more layers you add. And so this is what we do here in Python. We're taking for all of our layers, we're going to feed that forward. We'll walk through this. And then we get the output. This is the matrix multiplication part. So we're taking the input, which is the features here. Inputs, features. So when I wrote this library, my own custom library from scratch years ago, and I made it so that I can have different kinds of layers, which is common when you see in most machine learning frameworks. They have varieties of kind of layers, like a dense matrix layer, or a dropout layer, or a CNN, or an RN, or LSTM, or you name it. Lots of options there, right? Usually, I mean, the most foundational is a dense layer, which is just a matrix, just a very basic matrix. And so if we look at this forward, it is simply dot product for the weights, which is the matrix. This is the matrix right here. The weights is the matrix. Dot product from the inputs. And the inputs is the features, right? The features are our pixel data. This part right here is simply this aspect. Now we are doing dot product versus a matrix multiplication, so there are some summations that occur to get the result output. So instead of a matrix that looks like this, it'll be a little bit different. This @ symbol is programmed in the NumPy framework to do dot product, and that kind of looks like this. Let's check this out. When we're doing dot product on matrices, it kind of looks like this. It's a little more straightforward if we kind of look at it in a diagram perspective. You take the digits and you multiply them, and then you create a brand new matrix. And this is what the feed forward looks like. You can see that in code here. For example, we take, this is what it looks like from a Python perspective. We have 2 arrays. They are both 2-dimensional arrays. And they are shaped in a way that align to sort of this format. You can see one is vertical and the other is horizontal. And when we do a dot product against those matrices, this is the output. One thing to watch out for is that shape is really important. When you're doing matrix multiplications or dot products against matrices, they need to have matching dimensions. So you can see there's three rows here and 3 columns. That is required. So every step of the way, you can always output various shapes as long as the following matrice has the ability to be transposed, which means rotated, fed into using the same number of units based on its dimension. With this strategy, you can make ever so larger matrices as you want, as long as the input size can match the dimensions based on the rotation. And it's really just easy. It's like rows and columns. Just think of it like that. The rows need to match the columns in terms of number of count when you're doing matrix multiplications. And then you can just expand them from there. And then you can contract them as well. So it just requires an additional matrix multiplication. And then eventually you get down to a layer that's a smaller, and then you get your output, which are the answers. And that's it. There's one line right here. It's a lot to think about, but it really is that simple. There is another thing on here that I didn't cover, which is this activator right here. An activator is simply sort of, I call them a constraint, and this would be an activator right here. So tangent and sigmoid, these are common. ReLU, you may have heard of ReLU here. And what does that, I want to try that. Let's see what that looks like. Really what it's going to do is it's going to constrain the output between -1 and +1 with tanh, np.tanh. So you can see this is the output. Because our values are so large, doing something that we don't really want to see, and this is sort of a vanishing, we're losing data. So this is a common problem as well. If your input data is too large or your weights are too big, you have a chance to where you hit all the way up to the absolute maximum. And now this matrix is going to have a hard time learning. So what you can do is you can shrink your values. Now we have, and this is the input value. So you divide by 10. So you've got an image data, and you divide by, and you want to put it into a float, so that way you have a nice smooth input. And now this matrix can learn. We haven't covered the learning process yet, but we will here in a moment. Everyone says, oh, we don't really know how it works. It just magically does. With machine learning and AI, well, actually, I think it's pretty simple and straightforward. What we're doing with machine learning and AI is creating relationship maps. We're sort of expanding those relationships across multiple dimensions. You're familiar with 2 dimensions where you have a grid, and 3 dimensions where there's a cube, like we live in 3 dimensions. You can go even further with math in 4 dimensions, 5 dimensions, 6 dimensions, hundreds of thousands of dimensions. And what we're doing is we're creating these multi-dimensional maps that have correlations that can make leaps to answers, and then we optimize towards those answers. So see here, like for example, we have input data, like this could be image data, right? A set of pixels, a picture, and then we have, the sort of the memory, right? The layer weights, the parameters, which is sort of the brain or the memory, right? And then we input the data and we create a correlation map that generates a full correlation between every element. 2 times 4 is 8, 2 times 5 is 10, 2 times 6 is 12. So we've created this correlation map. And what we do is we can increase the dimensions and correlate those correlations even more by adding another layer weight, another weight or another matrix, multiple matrices. And this is the deep learning aspect. When we train that model, the back propagation is simply the same thing of feed forward, but we're feeding backward. We take our picture, we move it forward, we get an answer output, and say we're classifying an image to say it's a cat or a dog, something very simple like that. The final matrix output will be a smaller matrix, which will give us an answer of maybe it's a single digit, or maybe it's an array with 2 elements, like a matrix with just 2 values in it, a 0 or a 1. For example, the first digit could represent cat, the second digit could represent dog, and what we're going to do is we're going to optimize these weights right here to give us an output that matches what we're seeking, and that's done through back propagation. So step 1 when you're training a model is to run it forward through your layers, your matrices. You do the matrix multiplications, you get the outputs, and you return the final output after you've gone through all of your matrices. The forward process is simply dot product. You can also just do multiplication. So here, for example, we are running this algorithm right here, very simple algorithm, where our activator, which is 10H, our inputs, which are the pictures, and then the model itself, the weights, the matrices, and then we're multiplying and we get an output matrix, and then we will run that again through another layer weight, and then we can do another layer and another layer, and then we'll have a smaller layer at the output, which will be the target number of dimensions that we're trying to optimize for, which is cat or dog, for example. And it will give us an answer. For instance, let's take our labels. Let's create some labels. So the output, the target, the desired outcome that we're looking for. Cat equals 1, 0, 0. Dog is going to be our second unit here, so 1 like that. And then we could have nothing, like no, neither is detected, 0, 1. So now we have our logics, our labels, our outputs, our desired outcomes, the things that we want to train the AI to know. We can input an image, pixel data, run our correlations over the matrix multiplications, and then get the outputs that look like this. And it's really simple. So we have, those are our outputs, our output labels. And if we want to run, for example, say we have a picture equals, all right, so we have a simple picture that is 3 pixels. Sorry. All right, so we get a 3 pixel picture. All right, I updated the picture to add an extra dimension because we can feed in multiple pictures at a time. In this case, we're doing just 1, but we could add like several pictures. So this is our 3 pixel picture. Then we can add the weights, which is the parameters of the model, and that looks like this. And then we can do a feed forward. In this case would be picture dot product WE weight. And that gives us an output of the prediction of what it thinks is the answer. It's like this picture is 24% likely to be a cat, 30% likely to be a dog, and 30% likely to be nothing. Now, as you can tell, it's completely random, basically. There's no, it's just giving us a random answer because it doesn't know anything yet. We didn't train it. So what we can do is we can take this output and say we knew this picture was a cat, and then we can calculate how far off it was from the actual answer. So we can say picture at weight, dot product at weight, matrix multiply, and minus cat. And so now we can see that it is off by a lot because it should be a cat, but it doesn't know about these other things here. There we go. We did it We did it the other way around. Okay, so cat minus picture at weight, and it says that, hey, we're close on the cat, but it's not going to be these other things. So the idea is we want to promote or penalize the model on the weights. We're going to take this loss, we'll multiply it by a learning rate, right? So we want to decrease the overall, because we could do this in one step, right? We could say you're off by this much and apply this delta to the original weights, and then it would immediately know that these pixels is a cat. The problem is it's going to bounce around and it's not going to be able to learn which one's a dog or a cat or nothing. So we want to ever so slightly incrementally provide, here's a sort of the gradient or the loss, and then we want to back propagate, which is kind of going in reverse. So we'll take this and essentially update these layer weights by subtracting this value, or adding it in this case, because we're adjusting the weights. So that way, the next time we run this picture through, it's going to recognize that it's that much more likely to be a cat. So we simply add it in this case. So adding will subtract a little bit from the outputs because it's not a dog or it's not nothing, but it is a cat, so it'll increase the cat likelihood. And so we do that over and over and over, and we give it a whole bunch of pictures with a bunch of different labels. And then eventually this matrix right here will be able to tell whether it's whatever you're putting into it is a dog or a cat. And you'd think it'd be more complicated. And it can be. There's extra things we can do in different orders. You can have more layers, right? You can have more weights. You can add the number of parameters in the weight, so you make the matrix bigger so it can learn more. You can add activation functions, so that way nothing explodes or nothing. You have to worry about vanishing gradients or collapsing gradients, exploding gradients. You want to make sure everything's kind of smooth. But as long as your input values are clean and the numbers remain kind of smooth, you'll be able to train a model pretty quickly just using this kind of approach. And you can see there's not a whole lot of weights, but we could train this model and it'll be able to find a cat or dog. And everything you're seeing on the screen right here, that's basically it. It's just that when you get into the frameworks, they bring with it, like say TensorFlow, PyTorch, they bring with it a bunch of functions that make these kinds of processes easier, so you don't have to do it by hand. But obviously, if doing it by hand, there's not a lot there either, right? So that's pretty much it. Here's the back propagation step where you take, you just go backwards. So say we have one layer or several layers. You find, based on the loss, which is the first gradient that we have right here, we've got the loss. We're subtracting the delta of what the target label is. We run it backwards, which is another matrix multiplication. We save those gradients in each layer. So that way we can then, once we have all the gradients calculated, we optimize based on the layer gradient, the learning rate, and the weights, the parameters of the model. It's segmented like this, and so that way we can have multiple layers. You can do it different than the way I did it here. Very clearly, it's actually pretty simple and straightforward because we're looking at the math right here. There's two pieces missing from this picture here is the activation and derivative. The activation is like tangent and tangent prime, or the derivative tangent, which is undoing the activation. And those are also very simple. Here we go. All right, so here is the tangent function. So nice little tangent function, and the derivative tangent, which is 1 minus the square for each element inside the matrix. And this is done to prevent in really big numbers in the matrix. So like if we were to do this here and add the tangent, you can see it doesn't change a whole lot. It does smooth things out, but it doesn't do a whole lot because our numbers are already basically within the range of what we're looking for. When you get into bigger models, tangent is a little nice because it helps. It's kind of a nice guardrails. I think of it as guardrails. Although you could design your layer weights and your input data and your label targets in such a way where you don't necessarily need those activation functions. Another thing that's missing here is a bias layer that I didn't mention, and I had that implemented in a different way. This also helps adjust the plane in the multidimensional matrix. You can get something that like converges, but then you might want to move that convergence, and that's the bias, and that is also typical. It's just another matrix. So the idea is in all these AI models, it's just a bunch of matrices, and then how we leverage them against each other and using different patterns to provide good target outputs. And that's basically it. So we have our labels, we have our input data with the picture, then we have the brain of the operations, the weights, the parameters. We do a dot product, we get our output, we calculate the loss, and then we can back propagate that and then adjust the layer weights with the loss. Okay, here we go. We've done the whole picture. So here is our output label, our input features, which is the picture. This says whether it's a cat, a dog, or nothing. We know it's a cat, so we're going to train the model. here's the brain, the weights. We're going to calculate the loss and the learning rate, and then we're going to add that back into the weights. And here's the new weights. It's been updated. So we added a little bit to the cat column section, and then we took away from the dog and nothing section. So over time, this matrix is going to adjust if we keep running this in a loop. And then we also provide it more training data. It'll converge in a way that it will know whether it's a cat, dog, or nothing. It's actually pretty straightforward. You could do this with anything, any kind of data. It doesn't need to be a picture. It can be categories, right? You could do category labels. So it's like company size, right? 0 to 10, 10 to 100, 100 to 1,000. And those could all be representations of numbers of the input data. I think this shows like a pretty clear simplification of the process. Like I said a little bit earlier, bias is missing and tangent is missing, and this is a very basic approach. You need to do other strategies such as batching. This helps with preventing overfitting, prevents the model from helping it to generalize, as the idea is you provide it input data that it's never seen before and is able to accurately predict what that data is, right? So it's like, oh, there's a cat. I've never seen this picture before, but I'm pretty sure it's a cat. I really like this. This is very solid. It all fits onto one nice line really simply. Like I could, this is the only thing that's not a variable. I should just call that learning rate, right? I'd make another variable to call that learning rate. And then you just run it in a loop. You loop it over. And the idea is you have a lot of, you have all your labels, right? And then you just have a lot of pictures. And boom, you've created your own AI. And you did it from scratch. Well, you use NumPy. NumPy helps a lot because these are a bunch of for loops behind the scenes, but we don't need to worry about that.